Hello students, welcome back. Let us resume our discussion on orthogonality. Here's a definition of orthogonality. We defined vectors v and w are orthogonal if the scalar product is 0. When two vectors are orthogonal, we have Pythagorean law. Hypotenuse squared is equal to one side squared plus the other side squared. How do we use it? Here's one example. So u1, u2, u3 all the way over to un are mutually perpendicular unit vectors. In other words, ui dot uj is either 0 or 1. 0 when I and j are different, and 1 when I and j are the same. And this whole thing is often abbreviated into Kronecker delta, delta ij. And then each ci is orthogonal component, v dot vi over ui dot ui. In that case, c1 squared plus c2 squared all the way up to cn squared is less than or equal to v squared, as you saw in these kind of visualizations. You see, hypotenuse is longer than the side. Hypotenuse is longer than this green side. How do we prove it? For each I, we begin with this v minus c1u1 plus c1u2, c3u3 all the way up to cn un. This will turn out to be the orthogonal component vector, excuse me. This dot product of ui and do some brute force computation. Break up all the parentheses and you get v dot ui, and then u1 dot ui, u2 dot ui, u3 dot ui, all the way over to un dot ui. All those are 0 because they are mutually perpendicular, except, of course, ui dot ui. That's the only thing that survives. And then, please recall, ci is v dot ui over ui dot ui. Consequently, this denominator, ui dot ui and the ui dot ui, cancel each other out. And then what do you get? V dot ui minus v dot ui is equal to 0. How useful? 0 times ci is 0, so this times ci ui is equal to 0, and finally we are ready. Alright, next. Putting all the indices together, we claim this v minus this red, dot product of this red, is equal to 0. Why? c1 dot u1 dot product of this is equal to 0, as you saw before. And c2u2 dot product of this is equal to 0, as you just saw. And repeat all the way toward the end. cn un dot product of all this is equal to 0, as you saw before. So we have just a bunch of zeros added together. So this whole quantity is equal to 0, and that leads to this orthogonality. V minus this red is perpendicular to this red, and it'll turn out this is the parallel component vector, and this one is the orthogonal component vector, so to speak. And yeah, v minus this red is this brown, as a matter of fact. Here I use green, but now I regret changing all these to green because here I use red, and I don't want to change all these back into green. There are too many of them. Okay, now that we got this orthogonality, we can use this to set up a Pythagorean theorem here. V squared is v minus red plus red. subtracted and added the same thing, so no change here. And then from this orthogonality, we can use this first squared plus second squared is equal to hypotenuse squared. This equality comes from Pythagorean, and that works only because we have the orthogonality. Alright, the hardest part is now done, and then the next. Drop this one out, and this is non-negative quantity. It can be either strictly positive or it can be zero. If it is zero, there are no change, so equality. If this had been strictly positive, it's going to go down strictly. So either way, we have less than or equal to that. And then from now on, this is easy. Just another Pythagorean, repeated use of Pythagorean basically, because all these are perpendicular to each other. Repeat, and then we have C1 U1 squared plus C2 U2 squared, everything. And then take all those scalar multiplication out. And please recall, U1, absolute value of U1, or the norm of U1 squared is 1 because these are all unit vectors. So we have C1 squared plus C2 squared, all the way up to Cn squared. So V squared, in terms of norm, is C1 squared plus C2 squared, all the way up to Cn squared, which is, as a matter of fact, the length of the green vector. We see here, or maybe it'll be harder, but here. Just 2D version case. And let's just run it again. Okay, even though we proved it in a previous video, and I thought it is better to do it again, and I'm reasonably certain that I can cover 2.7 even after this, so let's go ahead and do that. Next, 2.7 orthogonal projection theorem, and this one is slightly harder, but it's a bit more important in terms of the application. And the application I mean by application outside mathematics, especially statistics and some physics, especially quantum physics, but there are many other applications as well. And here's a visualization. You see, so vector v is arbitrary vector, and c1, v1, c2, v2, all this linear combination is actually a parallel component. And v minus that parallel component will give me the orthogonal component. So this vertical. So length of this vertical is this norm. Does it make sense? So it's kind of like this one. Orthogonal component vector, all right. Visualization, all right. Okay, v minus parallel component, that's this brown vector. That's the orthogonal component vector, and that's this vertical here. Now, here look at this right-hand side. Here, instead of taking those C1 through Cn given by the parallel component, take A1, A2, A3 all the way to An arbitrarily. So it's arbitrary, so in this case it went over here. And if I run this program again, it'll change again. It may go over here or there. I don't know until I run it again. In any case, it's arbitrary. So what do you get? Subtracting v from that, I'm getting this slanted line. If I subtract like this, I get this straight vertical. If I subtract like this arbitrarily, and then we have slanted. Which is shorter? Of course, this is shorter. You're looking at it. Let's run it again. And then this is arbitrary, so this isn't changed. And this one is strict, so the same. So this vertical versus this slanted. Which is longer? Which is shorter? Let's run it again. Which is longer? This is pointless, right? Every single time, this vertical must be the minimum, and that's what this theorem is talking about. Of course, this may not be the best picture because we are looking at just, one vector here. That's because we want to visualize it in a plane. A little bit harder version is the 3D version here. So this time we have V1 and V2, up to V2. None of those, we have V1 and V2. In that case, we have something like this. So we have given vector V, and this is parallel component, and then V minus this parallel component, that's going to be this orthogonal component vector, and the length of this straight vertical, that's the left-hand side. This left-hand side is a straight vertical here. And green part is arbitrary, and then take this subtraction, this is just slanted, green, and which is shorter? It's clear, isn't it? Let's run it again. Okay, how about this? This is straight down. That's this part. And then right inside this A1, A2 all the way up to AN, those are arbitrary. So this time it went like this, and this slanted. Which is longer? Which is shorter? Run it again, it's going to be the same thing again. So basically what we want is to prove that this orthogonal component is the smallest, or this parallel component here is the best approximation of V because the difference is the smallest, right? So consider this kind of situation. V is an infinite dimensional vector that I want to approximate with 10 dimensions. And then we want C1, V1, C2, V2, all the way up to C10, V10. And if you select those as these parallel components, then that's the best approximation, because any other approximation will give you bigger error, as you can see from this, if you prove it. And this is quite useful because in statistics, bounding the error is always a big deal related to principal component analysis and whatnot. And in quantum mechanics, we often deal with infinite dimensional spaces there, and somehow we have to approximate it to finite dimensional. We do this all the time there. And there may be other applications as well, but they can go really deep really quickly, so let's not talk about this any longer, and let's just move on. Okay, all right, here's the proof, and let's begin. Ready? For each high, we'll simply take this orthogonal component vector dot product of Vi. And we claim that Vi times that orthogonal component vector is equal to 0. Well, we have done it before, except that we used Ui before instead of Vi. But in case you forgot, all right, here we go again. V minus that dot product of Vi, and then we just break up all the parentheses. V dot Vi, and then V1 dot Vi, V2 dot Vi, V3 dot Vi, all the way over to Vn dot Vi. They're going to be all 0 because V1, V2, V3 all the way up to Vn, these are all mutually perpendicular. But there's one exception, of course. Vi dot Vi is, of course, 0. Excuse me, Vi dot Vi is non-zero. That's the only non-zero. Everything else is 0. So dropping all those zeros, we get that. And the Ci is equivalent to V dot Vi over Vi dot Vi, because that's the parallel component. And then please note these two cancel each other out. And what do you get? V dot Vi minus V dot Vi, and that's 0. Okay, because this is 0, we can multiply by any component, any scalar, excuse me. Ci minus Ai times 0 is equal to 0. Previously we had just Ci, but this time I'm using Ci minus Ai. Idea is the same. This times 0 is 0. Now putting all these together. C1A1 V1 plus C2 minus A2 times V2 all the way up to Cn minus An times Vn, dot product of the same thing, the orthogonal component vector. So what do we have? This dot product of that is equal to 0. We just saw that. Next, C2 minus A2 times V2 dot product of this has to be 0, as you saw before. Repeat, repeat, repeat. In the end, Cn minus An times Vn dot product of this has to be 0, as you saw before. So what do we have? We have a bunch of zeros added up together, so we have to have 0. And consequently, this vector and this orthogonal component vector is perpendicular. So we have it. We're going to use this, and we're going to set up the Pythagorean theorem. Ready? Okay, here we go. This right-hand side we are working on blue minus green, but let's insert minus red plus red. Consequently, I didn't change anything. Blue minus red plus minus, blue minus red plus red minus green is equal to blue minus green, because this is just adding 0. But then again, this and that are perpendicular. This part, C1 minus A1, V1, and C2 minus A2, V2, all the way up to Cn minus An, Vn, we saw before. So we have perpendicular vectors, this part and that part, so the Pythagorean theorem applies. We have the equality here. Okay, and finally, drop this part. This is non-negative quantity because it's squared. And if it is 0, then we have equality. If it is strictly positive, it'll decrease. So what do we have? This is greater than or equal to that because we just decreased something. Isn't that something we wanted to prove all along? That's greater than or equal to this. Oh yes, indeed. That's what we ended up getting. So there goes the proof. So we went through two theorems here, orthogonal projection theorem, compared with orthogonal component vector and the arbitrary subtraction. This is the smallest, or in other words, this parallel projection vector, this one is the best approximation of V, because anything else will give you bigger error, as you can see from this inequality. So any kind of optimization is actually useful. And we reviewed this one as well.